Hello, good morning. Thought we'd try out a video this time around rather than me posting just kind of a copy of the notes, which I think some students told me was not super effective. So I thought, why don't we try a quick little video, this thing that I've been telling you about for most of the year, and we'll see how you guys do with it this morning. Hope you guys are doing well, and I hope the block goes well with finishing this and then also doing a bit of practice afterwards just to get ready for your quiz next class. Cool. I'll upload this to my YouTube channel afterwards. You absolutely do not need to join the one subscriber that I have. I actually don't know if they're still there. They might have unsubscribed. You can just kind of click on the link on our Teams, watch the video, and then kind of get on with what you are doing in math class there. So here we go. This is the end of our notes. We have essentially two questions, example 4 and example 6, that I wanted to talk to you about, and I'm going to do this fairly quickly. Just because if it's too fast, then you can always go back and rewatch parts of this if that's going to help you. But I also don't want to make a super long video for you to have to stare at a phone for. So here we go. Let's talk actually about example 6 first, just because it's kind of connected to what we were doing and it doesn't make us kind of interpret like a real world problem. So if we are looking at example 6, then we have a question that says, given that sine theta equals 4 over 5, determine, we have cosecant theta, we have cotangent theta. So those are two of kind of our new reciprocal trig functions. And then the last one here is the value of theta. So what is the angle, and then give it also in radians, which is of course kind of our focus right now. So we know that sine theta equals 4 over 5, and I think the first thing that I want to do before I even answer any of these questions is I want to put this kind of into like standard position here, and I just want to draw a triangle that has a sine of 4 over 5. And so if we're talking about a triangle, we're talking about an angle here, and it says the sine, which is opposite over hypotenuse, is 4 over 5. So we know that the opposite side is 4, the hypotenuse is 5, and that means, like if you do a really quick Pythagoras thing here, then you know that 5 squared minus 4 squared, and the root of that actually equals 3. And so you know that your missing side here is 3, just in case you also wanted what's called the adjacent side. So now we can kind of answer any trig function, right? We can answer sine, cosine, tangent, and cosecant, secant, and cotangent if we want. We just kind of have to interpret what those mean. So first we have cosecant theta, remember, is the reciprocal of sine theta. So another way of writing that, actually a better way of writing that in this question, is instead of opposite over hypotenuse, this is just going to be hypotenuse over opposite. And once you know that, then you know that you just can read the numbers off of your triangle there, and the hypotenuse is 5, the opposite is 4, and that's the value of it. You guys can probably hear a sick little boy, Aiden, in the background playing with some blocks. He might come over and listen to some math in a minute. So that's how we do cosecant theta. Again, as simple as just making the triangle and then interpreting what the meaning of cosecant is. And you can just think about it as the reciprocal of sine theta. Then we have cotangent theta. Actually, very similar idea. This is the reciprocal of tangent theta. And again, another way of thinking about that is instead of tangent, which is opposite over adjacent, we're going to flip that, and it's going to be adjacent over opposite. That's a reciprocal. And so we've already created this triangle with the opposite and adjacent on it, and so we can just read the values. The adjacent is 3, the opposite is 4. So we're going to do 3 over 4, and that's our cotangent. That's the value of cotangent. Finally, we have question C here, which is what is the actual angle? So now you've created a few things here, right? You have equations that you can solve. And let's just you can take either of them, but let's take this guy, because I think people find it maybe a little bit easier to think about sine at the beginning. So we have cosecant theta equals 5 over 4. You'll notice fairly quickly that your calculators probably don't have cosecant and secant and cotangent functions on them. And so actually, if you want to answer this question, you should turn this back into the sine function just so that you can access the buttons on your calculator. And of course, when you do this, it's the reciprocal, and so just flip it, and it's 4/5. And this is the question, right? They told you that in the question. So if you wanted to just read that off the question, then you could do that. And then so to find the angle, you go theta equals the inverse of 4/5. And if you put that into a calculator, I think, let's just do this really quick. Inverse sine of 4/5 gives us 53.13 degrees. That's a wonderful answer for the angle in degrees. We should also put this in radians. So a lot of ways that you could do this. You could just take your degrees and you could multiply it. We talked about this in class, but you can multiply it by your conversion factor, and that will give you an angle in radians. Or you could just switch your calculator into radian mode and type in the same thing and see what it gives you. And so we're going to do the inverse sine of 4/5 again. This time my calculator's in radian mode, and it says 0.927. So a little bit less than 1 radian. And that makes sense. If you remember the video, actually, the video, I think, said that 1 radian, the very end of that video said 1 radian equals about 57 degrees. And so because we're a little bit less than 57 degrees, we should be a little bit less than 1 radian. And so that, in my mind, that equates and works out fairly nicely. And that's kind of how you access question example number 6 there. So cool, hope that works out. Let's go and chat about example number 4. This one's a little bit different and much more related to your math lab in 8.2, where we're talking about circles that have a different radius. In this case, a merry-go-round that's moving a certain distance over a certain amount of time. And so let's draw this first maybe. It says a merry-go-round has an approximate speed of 1 revolution per 20 seconds. It has a radius of 5.6 meters. So right away, that's what I want to draw. There's your merry-go-round. You okay, buddy? There's your merry-go-round. We have a radius of 5.6 meters. And it takes 1 full, so if you're a rider and you, for example, get on at the bottom, or actually let's just define it right here at the side. If you get on there, it takes 20 seconds for you to travel around this whole thing. I'm not going to leave that in the diagram because I think important thing to like note, but maybe not a valuable thing to draw in our diagram. Okay, and so it says, what distance does the rider travel if they complete 1.5 revolutions? And probably to do this, you want to figure out the circumference of this circle, which is the distance that the rider travels when they make 1 full rotation. And circumference of a circle is 2 pi r. You have a couple options here. You can either keep the value of pi in here. That's what I'm going to do in this whole question, actually, just because it's good practice. You also could just plug it into a calculator as 3.14 and get an actual decimal value of this. But I'm going to hold pi as pi rather than 3.14. So we have 2 pi times r. R is 5.6. So the total distance around this circle is 11.2 pi meters. That sounds weird, but again, 11.2 pi is just a number. It's like probably approximately 40. And we're talking about meters around the entire merry-go-round. And in this question, it says that the rider does 1.5 revolutions. So we just want to multiply 11.2 pi times 1.5 because they do 1.5 circles. And again, if you're keeping this in with pi, then you end up getting, what do we get? 5.6, 16.8 pi meters. And if you want the answer as like a decimal, then substituting 3.14 in, you get 52.75 meters. But again, I encourage you to keep pi in your answers when you can. It says here, in radians and degrees, through which angle will the rider travel if they stay on for 16 seconds? So this is a nice question to practice this idea of proportions. And so kind of listen to how I do this here. This is, again, is a very valuable thing to be able to do. So it says the rider is going to stay on for 16 seconds. Okay, so we have 16 seconds. I'm going to create a fraction here, part of a whole, right? 16 seconds is part where the whole circle takes 20 seconds. So we know that the rider will have gone through 16/20ths of a full circle. And we're talking about degrees here. So if you want to talk about degrees first, then you can do 16 seconds out of 20 seconds is equal to how many degrees out of a full circle. And so if you create that, then the calculation actually is fairly straightforward. You just do 16 times 360 and then divided by 20, and it gives you 288 degrees. Likewise, if you wanted to do this in radians, again, set up a proportion. You can just say 16 seconds out of the whole circle is equal to how many radians out of the whole circle, right? So again, to calculate x in this case, because it's radians, we're just going to multiply both sides by 2 pi, and you end up getting 32 pi out of 20, which reduces down to 8 pi over 5. And I think if you had done, again, the like kind of direct conversion using the measurement formula, then you would have ended up with this as well. So a couple ways for you to kind of access that idea. Okay, the next one, what distance will the rider have traveled in those 16 seconds? So identical question, except this time instead of an angle, we're talking about a distance. So they've gone 16 seconds out of a full circle. So how far will they travel out of the full circle's distance, right? So 16.8 pi. So again, part of a whole equals part of a whole. On the left side, we're talking about time. On the right side, we're talking about distances. So x here, when you fire this into a calculator, and I wonder, just because we're using a decimal here, I'm going to give this to you both as, let's see here, both as 13, so it says 13.44 pi meters. Or again, if you're not holding pi in your answer, then this is going to be 42.2. And I like that as an answer. Again, just making things kind of work out in my mind, because I know that the full distance around the circle is 52 meters, and I've gone about 3/4 of a circle, and so 42 seems like a kind of accurate number for how far I've traveled. Okay, and then the last one here, I think some of you are not going to like this very much, but we got to really dial this back to grade 11 trig. This last question says, how far from his or her original position is the rider after 16 seconds? As a straight line, not as an arc of the circle. If it was an arc of the circle, that would be fairly easy. You would just actually subtract 42 from 52, and that would be the remaining distance. But because it's asking as a straight line, then you have to kind of check out this idea. So the rider traveled 16 seconds, or 288 degrees if you want to think about that, or 3 or 8 pi over 5 radians if you want to think about that. But whichever way you think about it, it creates, the rider traveled about this far. After having started, sorry, I should have put this in, after having started maybe there, right? If you want, rider traveled this far. The one that I drew before was kind of like the angle of it. This is the actual distance of it. And we know that the circumference of this circle is the radius of this circle is 5.6. That means when they ended up here, they're still 5.6, like as a length away from the origin. And we're essentially being asked to find this straight line distance. So we have this triangle, right? I'm going to pull this out. We have this triangle. It looks like this, with an x here, a 5.6, a 5.6. And we know actually all the angles of this as well, believe it or not. So if you know that this is 288, this one going around, Then to finish the circle, this angle right here, it has to be 72. So this is 72. And because you know that one, and the two sides beside it are equal, then you know that this is the type of triangle where these two angles have to be equal. And how do I know that? Well, this angle opens up to 5.6. This angle opens up to 5.6. So they actually have to have the same angle measure. And because all three of the angles have to add up to 180, we can do 180 minus 72 gives us 108, and divided by 2. And so we know that each of these angles equals 54 degrees because they have to be equal. And once you know that, and you recognize that this is not a right angle triangle, you can't use basic sine, cosine, tangent stuff, then you can now be like, hey, I know two sides, I know three angles, I can fire in sine law or cosine law to solve this. I think sine law, when you have the choice, is often easier. And so sine law is sine of an angle over its opposite side equals sine of a different angle. This is another form of a proportion. Not that I mean to like preach that a whole bunch, but sine of another angle over its opposite side. And so you just like kind of pick two angles to work from. So I'm going to do maybe this one here, sine of 54 over 5.6. Sine of 54 over 5.6 is equal to, I'm going to use this one, of course, because our variable's in there, is equal to sine of 72 over x. And to solve this, x equals 5.6 times sine 72 over top of sine 54. And when you plug that into a calculator, you get 5.6 times sine. This set of notes, by the way, is taking longer than I wanted it to, but I hope it's making sense and it's giving you like a little bit of extra thinking for, why is it a negative? A little bit of extra thinking for just studying for this quiz that's coming up. So 5.6 times sine 72 equals that, divided by sine 54. Oh, because I'm in radians. Shoot. 1.75. That doesn't make any sense. Okay, I'm going to put this back in. Sorry, I was in radians. 5.6 times sine 72. Yes, that makes sense. Divided by sine 54. Cool. Gives us 6.58. 6.58 meters. And if we look at the triangle, that looks like a fairly reasonable number for how I've drawn it. Cool. So that's how far you are away from where you started. Thank you guys. I hope that helps in whatever way you accessed it. I hope it helps. And we will see you hopefully on Friday for your quiz. Take care. Bye-bye.